Hello everyone. I wanted to solve a problem from the Chapter 3 homework set. They give us here a system of three equations and three unknowns, a 3 by 3 system, and they ask us to determine k, which is right here, so that the system is dependent. Now obviously to run this one to a happy conclusion, you really have to know the definition of dependency, and that causes a lot of trouble. Hopefully when I'm done, you'll be very clear on the idea. The way I wrapped my head around it was to rethink the word dependent in terms of a more common English term. Dependent really means redundant. And most of us know what redundancy means, but let's bring in the dictionary definition just to clear that up. When we say something is redundant, it's characterized or containing an excess. So a system that is dependent is redundant in that it has an excess of equations. It has more information than is needed. I'm going to actually get redundant about this whole thing by creating a system of equations, a simpler system of equations than the one in this problem, so that I can really hammer the point home. It is three equations, but I've eliminated the z variable, so it's three equations and two unknowns. I'm hoping for you something immediately jumps out at you, namely that this second equation is really the first equation multiplied by 2. So it is a redundant version of the first equation, if you will, a clone of the first equation, and adds nothing new to this system. In essence then, this is a dependent system. What I did here was I went to Wolfram Alpha and solved this system. So here you see it. The three equations, and I hit return, and Wolfram Alpha tells me the answer is x is equal to 3 and y is equal to 1. In other words, the ordered point 3, 1. First, it's very easy to see that 3, 1 works right here. 3 plus 1 does in fact equal 4. I'm not going to even check it in this second equation because it's just the first equation, and I've already checked the first equation. This is just a redundant version of that first equation. The third equation, however, we need to check it, and we can see that 3 minus 1 does in fact equal 2. So 3, 1 is the solution, and the system itself is dependent, and we can see that even more clearly here in Wolfram Alpha. What I'm going to do here is eliminate this middle equation, the redundant one. Now, theoretically, we should still get the same answer. So I hit enter, and lo and behold, Wolfram Alpha gives me the same answer, 3, 1. So this is in fact a dependent system that has a solution. What we're looking at here is a dependent system that had a solution. Now what I'm going to do is tinker with this system ever so slightly. Here it is again. It is identical. But the third equation I've changed ever so slightly. This minus sign I've made into a plus sign. Other than that, these two systems are the same. But that turns out to be a fatal change because this first equation says two numbers add to 4. And this third equation says those same two numbers simultaneously add to 2. You can't think of two numbers that simultaneously add to two different things. And so this system here, even though it's a dependent system, it has no solutions. Let's bring in Wolfram Alpha. Here's our original dependent system. I'm going to change that minus to a plus. That was the fatal change. And now when I hit enter, watch what happens. No solutions exist. And so what we have here is a dependent system that has no solutions. A system can be dependent and have a solution. It can be dependent and have no solution. So there's two questions here. Whether a system is dependent and then whether or not that system has a solution. And that's where things get tangled. Fortunately here in this problem, they only asked us to find a dependent system. In other words, we want to find a k here that makes this thing a clone of these above. And you can play around with this, trying to generate this third equation from these other two. And it turns out to be quite tricky. There's really no easy way. It's not a multiple of either one of the two equations above it. In fact, the trick is you have to add the first and second equation. Here are the first two equations, and I put an addition bar there. Now when I do that addition going down, I'm going to get 3x. And then my minus 3y plus y is going to give me a negative 2y. The plus 2z and the negative z is going to give me a positive z, and the 3 and the 1 are going to give me 4. Now this equation right here depends or is a redundant version of the two above it and adds no new information to the system. Once I've created this redundant equation, I see I can get to that third equation by multiplying it by 3. This equation is identical to this equation, and that this equation here is in fact a redundant version of the two above it. I got there by adding equation 1 and equation 2, and then by multiplying that result by 3. So this equation adds no new information, and it tells me that if I let k equal 12, I will have created a dependent system, and that is the answer. Whether or not this dependent system when k is equal to 12 has a solution or not is another question entirely. What we've done here is create a dependent system. We did that by adding the two equations above and then multiplying that result by 3. So I hope you're a little firmer on the idea of dependent. It is a redundant situation. When I let k equal 12, this equation here becomes redundant.